That was back in the late 90s, and what was really cool was this holistic notion of the human motion. We also didn't have a large database. You have a small number of examples, so it's not sort of the large discriminative database learning kind of stuff that goes on in action recognition now. What we're going to do next time is we're going to take a look at a different approach that takes looks at video as a time series analysis, and just some basic approach to doing that. And again, this will be something where, much like the SVMs that we just talked about, we said it can only give you a small taste of it, and if you want to know more about it, you should take a course in machine learning. We're going to show you a very simple notion of a form of a graphical model approach to doing action recognition. And if you want to do more of that, again, you'll take machine learning. But that's what we're going to do next time. All right, welcome back to computer vision. Today we're going to talk a little bit more about some activity recognition methodology, technology. In particular, we're going to focus on time series. And mostly we're going to, this part's going to be on something called our Markov models and its way of representing time series. And then we'll talk a little bit about how that is applied to vision. So here is what's referred to as an audio spectrum. And at the top up here, that's a waveform. That's the actual signal coming in. It's voltage as a function of time going into a speaker. And what this is what's referred to as a audio spectrum, short-term Fourier decomposition. Basically, you've got low frequency stuff down here, high frequency stuff down here, with time going that way. And the question is, that's a sound. What sound is that? Obviously, it's the song spectrum. It's the spectrum of the prothonotary wobbler, or warbler. Obviously, I'm not a bird person, okay? There's a picture of one. But the idea is, if you listen to this bird chirp, and then you process it over time, or actually, you listen to it chirp over time, and you process it, you would see this audio spectrum. And the spectra of different birds, of course, are different. Here's two different birds, the prothonotary warbler and the chestnut-sided warbler. But what you can see is that the spectra are really quite different, right? And the goal is to think about these things as what's referred to as time series, and how would you distinguish between them? So for a given time series, there are questions you can ask, like, which bird is this, okay? So you've got an audio signal. Which bird is it? How long is this thing going to keep going? Is this bird sick? Right? That is somehow not normal. And are there different sort of elements or different phases that the bird has? And when you think of these in a time series context, which bird it is, that's a classification problem. Time series classification. How long will it continue? Might have something to do with prediction. Is this bird sick? Would be an outlier detection. And finally, you get a notion of segmentation. So that would be for like bird data. Well, how about other time series data? Here's some. So, here's stock data of different types of indices over different amounts of time. And you might have questions that you would ask like, will this stock go up or down? Something we all want to know. What type of stock is this, right? If you had a set of categories of stocks. And is this stock behaving the way it normally does? And that becomes just like we saw before, prediction, classification, or outlier detection. Here's another example. Suppose you were listening to the audio of this music, right? So not looking at the imagery of the score of the music itself as shown here, but actually listen to somebody playing it. You might ask things like, is this Bach or Beethoven, which would be classification? Can we make more of that? That's now a generative model kind of question. And computer music people are always interested in listening to some music. Could I have a machine produce more music of that sort of type? And can we sort of divide this up into segments? So this is what's referred to as time series segmentation. By the way, this bottom one is segmentation has received a lot of attention lately, something called conditional random fields being applied to it. We're not going to talk about that. We're going to talk about Markov models, but I just wanted to point out that you might not use what we're going to learn today so much for segmentation as much as you would for some of the classification things. All right, so you might ask, get ready, Megan, you might ask, what does this have to do with vision?
What does this have to do with vision?
Well, you might have some video of something happening, such as a person moving their hands around to wave or point or control something. And you'd like to be able to say, which gesture is this? Or, what action are they doing? And the stuff I'm talking about today is sort of some of this time series work, in particular Markov models, apply to the decoding of visual kinds of information. So the real question is, how do we model these problems? How do we, how are we going to build? I showed you these time series. Well, we need a model of these. And in particular, we're going to have to, given a bunch of them, be able to construct that model. So it's basically going to be an inference or a learning problem. The learning is learning the model, and the inference is, well, given a set of models, which one do I think is most likely to have generated the data that I'm seeing? So now let's talk about Markov models. And my apologies if you already know what Markov models are, because we're going to go through this a little bit. Then we'll get to HMMs, and maybe that'll be new for you. And if it's not, you can just write in a postcard telling me that you're unhappy. Send it to Megan. All right, we're going to pretend for the moment that weather, as in the weather outside, is a Markov model. And if it were, we're also going to pretend that there's only 3 types of weather you could have. You could have a sunny day, a rainy day, or a snowy day. It's kind of like a little kid's book, right? And a Markov model says that we have to specify for any given one of these, what's the likely next day going to be? So for example, suppose I tell you that if it's sunny today, there's an 80% chance that it'll be sunny tomorrow. 15 that it'll be rainy, 5% that it'll be snowy. Likewise, if it's rainy, I may tell you, well, there's a 60% chance that it'll rain tomorrow if it's raining today. There's only a 2% chance that it'll be snowy, so it's a place that gets very cold, so once it's raining, when it's raining, it's not going to snow, and vice versa maybe, and 38% it'll be sunny. And likewise, if it's snowing, there's a 20% chance that it'll keep snowing, 75% chance it'll be sunny, and for the same reason before, very unlikely that it'll rain. This is referred to as a Markovian system, and in particular, if the only thing you need to know to make a prediction about what the weather tomorrow will be is what the weather today is, that's referred to as a first-order Markovian system. So I don't look at today and yesterday and the day before. I'm just looking at today in order to make a prediction about tomorrow. If I was looking at today and yesterday, that would be a second-order Markovian. All right? So the probability of being in a particular state, of getting to a state, depends only on the state I'm currently in. In order to specify our Markovian model, we need a couple of things, right? So we need a set of states, and these are labeled here as S1 through Sn. And those, the S's, there's state 1, state 2, that's not a particular time or particular day, there's 3 different states. So in this example, N would be 3. We also need transition probabilities, and that's written as Aij. So that is the probability that if you're in some state I, that the next time you would be in state J. And then finally, to kick things off, we need an initial distribution. That's just the probability that Q1, and I'm going to talk about Q a little bit more in a minute, that Q1 is equal to Si. So Q sub t is whatever state I'm at time t. So Q sub 1 is the state at the first day, or time 1. So for this particular example, as I showed you here, you've got 3 states, sunny, rainy, and snowy. We've got these state transition probabilities. So this matrix A, that's the encoding of all of these links, of all of these transition values. And then I have an initial distribution which just says, well, to start off with, maybe 70% chance that it's sunny, 25% chance that it's rainy, and if my math is right, 5% chance that it starts out as being snowy. So given this Markovian model, you can ask certain questions. For example, you could say, if I give you this series, so that's sunny, rainy, 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 snowy, snowy, you could say, what's the probability of getting that series? Okay. Well, you have all the information you need. In fact, it's written down here below. I've got A and pi, right? It's just the probability that I start out sunny, that's here, times the probability that it becomes rainy given that it's sunny, so that would be here, times the probability of rainy given rainy, which is there, all the way through. I just have to chain it through, right? And when I multiply all those numbers together, 0.7 times 0.15 times 0.7, blah, 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 I get some number, 0.0001512, okay? They tend to be small numbers, by the way, probabilities in HMMs, or in Markov models, because whenever I multiply a lot of numbers that are probabilities together, since all numbers that are probabilities are less than or equal to 1, when I multiply a lot of them, I get small numbers, and when you implement these things, you sometimes have to be careful and do things like take the log, but that's all I'm going to say about that. All right, so that's a Markov model. But much more interesting than a Markov model for what we're going to do is what's referred to as a hidden Markov model. So here's the basic idea. Suppose you actually can't observe the state, okay? So there's some state doing its thing, but you can't observe it. But what you can observe are what are referred to as observables, or the evidence. So let's suppose for the same weather example, okay, let's suppose the things that we can observe are essentially what women of the day happen to be wearing or carrying. So maybe I see this very chic bathing suit on a person, or I see just a nice coat that could be worn anytime that it was sunny, or an umbrella. So these are the evidence of what the state is. So before I can go further, I have to tell you one more thing about our Markovian system, and that's what's referred to as the emission probabilities. Emission, if you think of it as symbols being spit out. And the emission probabilities are written like this: B sub j of k, and what that means is the probability that you'll see symbol k, that you'll see a bathing suit, given that at some time you're in some particular state. Okay? So what's the probability you'll see a bathing suit given that it's sunny? What's the probability you'd see a bathing suit given that it's snowy? All right? Those are called the emission probabilities. And what that means, our entire system, when it's running, looks like this. In this new system, where we can't observe the states, we don't ask questions about the likelihood of having seen a particular sequence of states because we can't see the states. Instead, we're going to ask about the likelihood or the probability of seeing a particular sequence of observations. So that's shown here. So you could say, given this sequence of observation, coat, coat, umbrella, umbrella, bathing suit, umbrella, umbrella, what's the probability of that series, of that sequence of observations? Well, we could evaluate that if you give us everything, right? So here I've just written it out as P of O is this all the sequence of all the observations, and I know the way to compute that, and we'll get more of the details later, is I could say, well, if you told me the sequence of states, then I could tell you the probability of a given observation, and if I multiplied that by the probability of that sequence, I could get the whole thing. So one simple example is, well, one possible sequence of states, just one, is that it's all sun, right? And that can be determined from the yellow stuff here, right? So it's the probability that I start with sun, 0.7, right there, and then I follow that with a whole bunch of sun, 0.8, right? All sunny days. So this is the probability of all sunny days, and this would be the probability of seeing this sequence if every day was sunny, right? So the coat, it's a 0.3 probability. There's 4 umbrellas, and there's only a 10% chance of seeing an umbrella when it's sunny. Notice, by the way, I wrote 0.1 to the 4 here. The order doesn't matter, right? Because I'm assuming that if you tell me the state, that I can tell you the probability of having an umbrella. It doesn't matter what the day before or the day after was. You tell me that it's raining, I can tell you the probability that they're carrying an umbrella. But this was only for one particular sequence of all sun. You'd have to worry about all possible sequences of weather over those 7 days to talk about the probability of getting this one series. So to make that a little clearer and a little easier, let's just do the math. So to make this a little bit more formal, we're going to specify sort of all the elements of an HMM. You've already sort of seen them. N is going to be the number of states. So S1 through Sn is our set of states. So that's like sunny, rainy, snowy. And then there is a notion of a state sequence written as Q. And the idea is that Q sub I is whatever state I'm at time I. Okay? So when I say Q sub 3 equals S2, what that means is at time step 3, I'm in the second state. All right? Given the state, I can talk about the full specification of an HMM. And for whatever reason, HMMs are referred to as lambda. It's a triplet made up of 3 components that you've already seen. There's a state transition matrix. Those are the A's, the probability of going from one state at one time, given that you're at another state. There's the observation matrix, which before I was showing you as a discrete and was actually represented as a matrix. There's also a continuous version where your output is you have a distribution over some feature vector for each state. So maybe it's you're outputting some sort of measurement, and what you say is I've got one Gaussian in state 1 and different Gaussian